Hello and welcome back to day 8. So when I solved this problem today, I didn't see a whole lot of algorithmic changes that would sort of imply that we would want to start with TDD. So I figured today what we would do is we would explore a different agile concept. We'll potentially do some TDD, but really what I want to talk about today is how do I turn experimentation into production code. So in many agile processes, the idea of experimentation is formally known as a spike. And so what does a spike mean? A spike means I'm going to go write some code to understand a problem better that I don't understand well enough to sort of spec out what I want the final thing to be. Then I'm going to throw that code away or evolve that code into the production code. We'll probably focus a little bit less on the TDD part of it today and more on that code evolution part of it today. But the reality is when you're doing this, you would create your production version using TDD, but you might use unit tests in the meantime during your spike to sort of figure out what it is you know or don't know. So let's go ahead and take a look at the problem today. And we're going to take a slightly different approach when we're solving the problem, and you'll see. The approach we're going to take is very much like what I do when I'm solving these just to solve them. Okay, so day 8. You find yourself on the roof of a top secret Easter Bunny installation. While historians do their thing, you take a look at the familiar huge antenna. Much to your surprise, it seems to have been reconfigured to emit a signal that makes 0.1% more people 0.1% more likely to buy Easter Bunny brand imitation mediocre chocolate as a Christmas gift. Unthinkable! By the way, 100%. Easter Bunny chocolate, usually not good, unless you're buying a really expensive one. All right, so scanning across the city, you find there are actually many such antennas. Each antenna is tuned to a specific frequency to indicate a single lowercase letter, uppercase letter, or digit. So case sensitive, that's what you're telling us. You create a map, your puzzle input of these antennas, for example. So we have 2 different antenna frequencies here, antennas with frequency 0 and antennas with frequency uppercase A. Signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antenna. In particular, an antenna occurs at any point that is perfectly in line with 2 antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means that for any pair of antennas with the same frequency, there are 2 antinodes, one on either side. So here's an example. So what we see here is this A and this A. You can see it goes over 1 and down 2. So the first antinode would be twice that distance from here, right? Would be over 2 and down 4. So this one's actually casting this antinode. And then this one, twice as far a distance away, is this one here. Okay? That seems pretty straightforward. Adding a third antenna with the same frequency creates several more antinodes. It would ideally be 4, but 2 are off the right side of the map. So instead it only adds 2 more. So for example, we see here, this one is this antinode. The other antinode would be out here somewhere, right? And then for this one, this antinode, for this one, and then this one here. So we have to look at every pair, this one with this, and then these 2 together. So antennas with different frequencies don't create antinodes. A and A count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes, but has a lowercase a frequency antinode at its location. So this one was an antinode up here, but because it's an A, they still show it as an A. They're doing that for illustration purposes, but for us, for our count, we would count 1, 2, 3, 4. So we have to remember that that is now an antinode in addition to an antenna. Okay, so the first example has antennas with 2 different frequencies. So the antinodes they create look like this, plus an antinode overlapping the topmost A frequency. So there's an antinode here. Topmost A, right. So there's an antinode here. I'm not sure from where. Maybe, oh yeah, here, 0, 0A. So then the other one would flip off the top. Okay, good. As the topmost A frequency overlaps with the 0 frequency antinode, there are 14 total unique locations that contain an antinode within the bounds of the map. Calculate the impact of the signal. How many unique locations within the bounds of the map contain an antinode? Okay, so the first thing we're looking for then is 14. So what does our grid look like? So we've done calculations like this before with grids, and you have to remember not to go off the edges. So let's start with doing a file, read all lines. In the file name, we're going to select for each line. We're going to do 2 character array. We're going to turn that whole thing into an array. That's going to give us our double character array for the grid. The next thing we want to do is we know that based on this description that this A is actually a hash mark. And we want to be able to keep track of those hash marks so that we can count them later. So that means we can't count on the antenna staying on the map from a character perspective. So we really probably ought to find all the antennas first and then process all the antennas. So let's say, we're going to say locations by antenna. And this is going to be a new dictionary of character, list of int, row, int, column. Right? So that's going to be our locations. So the letter of the antenna will be the key. So that'll be like a 0 or an A. And then the list is going to be every 0 for zeros and then every A for A's. So that's what we need to do. So we need to walk the grid, find all those. So we'll do for var row in, let's say, nope, for var row 0. Row is less than grid length. Double plus row. We've written this loop quite a few times already. Column is 0. Column, come on, column is less than grid row length. Double plus column. Right, and then for each one of these things, we're going to say the antenna that's there is grid of row and column. All right, if the antenna is actually a dot, then we just keep moving on. Otherwise, we're going to say locations is going to be locations by antenna, add or get, right? We're going to use our wonderful little function here. We're going to do an add or get for the antenna. And to that, we're going to add our row and column. So that's our scan for all of our antennas. So now what we need to do, given that, what we need to do is we need to pair up every antenna with every other antenna of its type, calculate the offset, and start setting antinodes. So what's the easiest way to do that? The easiest way to do that is for each var location, let's see, KVP, because it's really a key value pair, in locations by antenna. Actually, we don't really need the actual antenna. So we'll just take the locations, right? So the values is going to be basically a value collection of list of locations, right? So location is going to be that list, locations. Okay, so given that, what we need to do is start where we are and then process every node after us. And the reason we want to do that is we're going to start at 0 and we're going to process 1, 2, 3, for example, if we have 4 antennas, right? And then we go to 1, there's no, I bumped the mic. There's no point in going back to 0 because we already did it. So we'll just do 1 with 2 and 3, and we'll move forward and we'll do 2 with 3, and we'll move 3, and then there's nothing left, and so we're done. So for each one of these locations, we're going to say location index is 0. Location index is less than locations count minus 1 this time, because no point in starting at 3 because there's nothing after 3, right? So we just want to start with 0, 1, and 2. And then we'll do this. So given this location, we're going to call this location 1 index. Because then we want to do location 2 index is location 1 index plus 1. And then this one, we want to go all the way to the end. Locations count location 2 index. Okay, so far so good, right? We're going to run over every location or every antenna for every location. We're going to find every other location to pair it up with. Now we need to know the direction in which we're going to add our notation, right? And so that is going to look a bit like D row is going to be location 1. Let's see. Let's get locations of location 1 index, right? And then we'll do location 2. So we're going to do location 1 row minus location 2 row. And then we're going to say column, the distance is location 1 column minus location 2 column. And then we need to basically set hash marks at the distance again away from each location based on this delta. So we'll do grid sub, let's do this. We're going to do set node. We'll call this location 1 row plus D row. Location 1 column plus D column. Right? And then we're going to do a set antinode. Then we'll do a set antinode location 2 row minus D row, because we need to go in the other direction now from location 2. Minus D column. That should be a plus up there. I don't know how we got an equal sign up there. And this set antinode is just going to be a little helper function. It's going to need the grid, of course. Grid. So we'll do set antinode. Given our grid, we're going to do a row and a column. And this is where we're going to do our bounds checking, right? Because if I just sort of blindly tried to push things into the grid, I would run over the edges one side or the other. So here we can say if row is less than 0 or row is greater than or equal to grid length, or row is less than, or column less than 0, or column is greater than or equal to grid sub row length, then we're not going to do anything. Otherwise, we're going to do grid row column is an antinode. Okay, so that should walk everything and get us our antinodes. Then the end here, the result is basically now just going to be, we've done this before, where we're going to select each grid row, and we're going to select each node and say, if you're an antinode, we want to count you, otherwise we don't. And then we're going to sum that together, and then we're going to sum that together. So we've written that line of code a couple of times now too. Walk the whole grid, find the thing we're interested in, and count them. And then we should get back our result. Okay. We're not skipping, so let's see if this works. I just wrote that real fast off the top of my head. We expected 14 and got 5. Okay, well that's not right. So what did we do wrong? Let's take a look at everything first. Right. So let's hit a debug breakpoint here. First thing we'll do is we'll look at our grid. So our grid looks like dots. There's a 0. So we see a 0 at 1,8. We see a 0 at 2,5. And now let's look at our locations by antenna. So here's a 0. We should see 4 zeros. And those are at 1, 8, 2, 5, 3, 7, 4, 4. Okay, so that looks good. We have read, right? We have read the grid. We've read the antennas. So far that looks okay. So now we're going to say for each of our locations there. Okay, so the first set of locations is going to be our zeros. All right, so that's 1, 8, 2, 5, 3, 7, 4, 4. That looks good. Okay. So we're going to want to set, if we look at this data, so we're going to look at these two first, right? So we want to set what it should be Okay, so we're down 1 and over 3. So down 1 and over 3 should be there, and then up 1 and over 3, and there. So those should be the first two that we're going to put into place. Obviously, I don't want to save that because I don't want that to actually be like that. Okay, so those locations, if we calculate them, by the way, so that would be 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 0, 11, and 3, 2. 0, 11, and 3, 2. Okay. Okay, so our first location is 1, 8. Our next location, oh, there's our problem. We have the wrong location index. All right. Let's go ahead and undo this because I'm going to run it again and see if everything works. Okay, now it works. Okay. That was a pretty easy problem to solve. So we've now figured out that we've got a sort of an experiment of exactly how would we go about doing this, right? Let's make sure that this applies to the big data set. And here's our big data set. You can see there's all kinds of antennas of all kinds of numbers. You can see, just to be clear, they definitely did put in like uppercase, lowercase difference. So the fact that we're being case sensitive is important. We see numbers and lowercase letters and uppercase letters and nothing else. So they didn't throw any curveballs into data. So let's see if we hit 390, which is what, when I did this, I got the first time. Okay, so that got us 390. Okay, so here's where I want to stop, right? We understand what we're doing here now. We've sort of figured out the best way to do this. Variable declaration can be deconstructed. So you could say row and column, except those are terrible names, right? Anyway, that's fine. So what are we actually doing here, right? So let's comment this up a bit. So we need to parse the grid. We need to find the antennas, right? Then we need to perform an action for every antenna pair. That's essentially what this is, right? This loop is find me every antenna pair and do something with it. And the something that we're going to do is setting antinodes based on calculations of this. Then we need to calculate the antinode count. Right? So those are essentially the 4 things that we need to do. So what I want to do is I want to postulate what an alternative API might look like here, right? So let's do this. We'll scroll this up and we'll say, I would really like to initialize a grid with file read all lines from our file name, right? And then I'd like to say per antenna pair, right? I don't know what these parameters are yet, so we'll come back to that. Right, and then I would like to say assert equal expected grid.antinode count. Right, that's essentially what we're doing up here. Parsing the grid, finding the antennas, performing an action for every antenna pair, and then calculating the antinode count. Implied in here is that the grid constructor understands the parsing of the antennas, right? So this, in essence, is our constructor. Find all the antennas. And we need to do that ahead of time, remember, because some of the antinodes are going to overwrite the antenna locations. And we need them to show up as antinodes in the list in order to be able to be counted. An alternative to this is the grid could store a list of antinodes. Right, it could use a hash set of antinodes. So every time you set an antinode, instead of modifying the grid, it would basically set that list, and then you can just count the hash set. That's an alternative. But I like this idea of, parse and find everything we need to know ahead of time, and then go ahead and perform the loop and mutate the grid as a result of this loop. I like that. That's what we've done in the past, so we'll continue to do that. So if I'm going to do a per antenna pair, what do I really need, right? Well, for starters, I need these two locations, right? So location 1, location 2. Think that's what I need. And then this is, what I'm going to do in here. So if we have a location 1 row, location 1 column, all of this, and then this would be, instead of a grid out here, right? This would be a grid set antinode. Okay, so given a particular row and a column, set the antinode. That's a pretty good first swag, I think, of a design of what this thing might look like. Now, if we were going to do TDD, using this as our guide, we would TDD our way into this class. Some people call this kind of turning the spike into, the final thing and then TDDing way through it is like, this would be an acceptance test, right? And so you're doing acceptance test driven development by defining the acceptance test. And then in order to evolve everything that you want out of, for example, the grid class, you would actually use traditional TDD to evolve that out of the grid class. We're just going to skip the TDD part today because you've seen some TDD. So let's go ahead and do this sort of acceptance test version and just give you the grid class at the end of the day. All right, so the first thing we need, obviously, is we need a grid. So let's start there, public class grid. And we know we need a constructor, which takes our lines. These are going to be our grid lines, right? And we know that this is, in essence, what we want out of that constructor. By the way, we're getting this because we need to call that like part 1. Okay. So this is in essence what we need. So we need to stash this grid, right? So we're going to do read only character double array is the grid. And okay, yes. So we don't need to do the file read all lines. That's going to be the grid lines. And then this is locations by antenna, right? So we can actually move this up here. Your read only. Really still getting used to this new keyboard. Right, you can start up here as an empty dictionary. And then we'll go ahead and find the antennas. Okay, so far so good. Yeah, go ahead, go away. I seem to make Visual Studio upset all the time. I'm amazed we've gotten all the way to day 8 before I really made it upset. Usually when that happens, I will restart it. But I'm not going to do that. All right, so we need an antinode count, and we need per antenna pair, and we need set antinode. So we need all of those things, right? Let's go ahead and do set antinode. I don't know why you think that can't be something that you could generate, but let's go ahead and just put it up here. Public void set antinode, int row, int column, right? And then we can just, where'd our set antinode go? It's up here somewhere, right? Yeah, it's up here somewhere. Where'd you go? There you are. Oops, I don't want to cut you because I want the other test to still pass, right? So I'm going to evolve this out, and then we can take that other test away once we're confident that we've got the new version that we like. All right, so there's set antinode. We need an antinode count, public antinode count. We know how to do that, right? That's this. Let's go ahead and do that. Our antinode count. Then the last thing we need is we need per antenna pair, and you're going to get a location 1 and a location 2. Okay. Public void per antenna pair. And what we need to take is an action of int row, int column, int row, int column. All right, that's going to be our callback. Okay, and then we have this logic here is essentially what we need. And we don't need these temporaries, right? We can just do a callback with locations of location index 1 and locations of location index 2. Okay, so that's per antenna pair. So really all we've done is taken all of our locations and put them out. I don't know why I have the word new there. That it was greening about. We've basically just taken all of our code out of our spike and moved it into the design we think we like better. I'm going to go ahead and roll that up so I don't have to look at it anymore. All this code is now compiling. The question is it going to work? And the answer is yes. Okay, so that's good. I expected it to work, right? Because in essence, we just took this test, moved most of its code up into this class. Now, this passing around of unnamed tuples, this tuple stuff here, I'm not a huge fan of that in production code. I know we've done it in the past, but what I'd really like to see is I'd really like to see a type here for this. So what I'm going to do is I'm going to make a new type. Right? So we're going to say grid location. Let's make this a record struct. So what we can then do is we can say int row, int column. Right? So that's our grid location. And everywhere where we see this, now up here, I would like to see grid location. Right? And so our action now is grid location, grid location. Okay, so that's good. And then all we need here is new. So we new up the grid location with the row and the column. Okay, that's not bad. We just need to come down here and these became uppercase because now they're properties and not, anonymous tuple names. But otherwise, this code should now work a little bit better. Okay. Still working. All right, I like that. We're getting a little bit clearer. What else do we need? I think at the moment, we probably don't need anything. I think we're okay. I am sort of interested in this. This is also something that I'm sort of interested in making better, right? So this is in essence, if we think about this, this is an offset, right? So if we were to say, let's say the code looked like this instead, okay? Offset 1 is going to be, again, we're inventing things here, right? So grid offset between location 1 and location 2. I'm going to go ahead and set an antinode at that offset. So what I want then is location 1 plus offset 1. Okay, and then I'll do offset 2, which is grid offset between location 2 and location 1. So now we're going the other way. We could not compute 2 offsets here, but instead use the other offset by just doing plus and minus, right? So we could say this is 1 offset, right? And then we'll do plus and minus. So let's do that. Let's make this now grid offset. And it's got a little static factory function. And we assume that that's going to be basically this, row delta and column delta. So let's now make public record struct grid offset. Offset, okay. Row delta, column delta. And now we actually need our little static function here. So let's do between one grid location, location 1, and grid location, location 2, right? And that would basically be, we don't even need that because we're just going to do this. We're going to make a new grid offset. Oh, by the way, you return a grid offset. We're going to make a new grid offset of location 1 row minus location 2 row. And then location 1 column minus location 2 column. Same thing we did down there, except now we're moving this up into this offset. And the other thing that we need to get this to compile, as we see our reds down here, is now we need plus and minus. So given a location and an offset, we should get back another location, right? So think about this like the datetime and datetime offset class, right? You have a datetime and a datetime offset. If you add an offset to a time, it moves that time forward. If you subtract the offset from the time, it moves that time backwards. So let's just go add those two functions. And in order to do that, what we do is we make public static grid location operator plus. So given a grid location and a grid offset, right? We're going to return a new grid location with location row plus offset row delta. Guess we could have called it offset. And then location column plus the offset column delta. So that's plus, and then we have minus, which is basically the same thing, except we do minuses. Okay. So now we can transform a grid location into another grid location given an offset. All right, so that's pretty good. So now our code down here, grid set antinode. Oh, set antinode is not taking our location class yet. Well, obviously we can fix that. Grid location. So what we're going to need here is instead of row, we have location row. Everywhere where we see row, that gets replaced. And then everywhere we see column, this is going to be location column. Okay. Then we have the column. Okay. I don't see any more red over here, so it looks like we're done. Does our test still pass? It does. Okay, so now when I look at this, test, am I happy with the APIs that I've created here, right? I've created this grid, I've created this notion of an offset, I've created this notion of locations inside the grid. That's pretty good. I can do one more thing, like this is interesting. A grid location should probably know whether or not it's inside of a grid, right? What was the easiest way to do that? Let's go with public bool is valid. And then we need a grid. For right now, this is the best we can do because that's all we have exposed down here in terms of what could we pass. Right, if we pass the grid class itself, then what we'd want is more parameters for it to check. So let's do this one step at a time, right? So we'll say if you're valid, basically the opposite of this test. So we'll go ahead and we'll bring this up here, but we're going to do the opposite, right? We're going to say we don't have to do location dot because we are the location, right? Then what we get to do is we get to say, we get to invert this, right? Actually, here's an easy one. Let's go ahead and put this back. We want a not around all of this, right? Because that's the broken version. And then we'll let the compiler, oh, you know what? I thought the compiler would allow us to invert this conditional. Yeah, okay, well, I guess not. All right, so row needs to be greater than or equal to 0, and row needs to be less than grid length, and column needs to be greater than or equal to 0, and the column needs to be less than the grid length. Let's see, maybe it wouldn't have, I don't know. I don't know why I wouldn't have done that. I sort of thought that the compiler would do that for us. So now down here, set antinode, we can basically say if location is valid for our grid, right, then we're going to do this. Okay, so that cleans that up a little bit and moves understanding, your validity to be inside here. Member can be made read-only. Okay, so that's interesting, right? So these things are effectively read-only structs, right? You can't change the row or the column, right? And therefore, this thing could be marked as read-only on a struct that could evolve, but that's unnecessary for us to do that because the whole thing is read-only, right? That's how we're treating this. Same with this one. You're also read-only. Okay. Now our test looks okay, and it still passes. We have made, we can make an assumption here on the grid about the fact that the grid is square, right? That it's not a jagged grid. And given that, we can say public int row count is going to be grid length, right? And then we can do public int column count. Going to be grid sub 0 length. Okay. And now this is valid for the grid will be us. So instead of passing the character double array, we can pass the grid. And then we can say row count and column count. Grid.column count. Okay. Now do our tests still pass? They do. Okay. Do I see anything else here that I want to evolve the description, definition of whatever this is? I think I'm happy with this. This looks really compact and nicely easy to use. We've invented a few types to make it work. What that means is I can now take part 1 away, right? And we'll go to part 1 alt is just plain old part 1. The set anti-node no longer necessary because it's been moved up into the grid class. All right, well, let's go see what's in store for us on part 2, right? So now that we have a design, how much does that design need to evolve? Let's see. Watching over your shoulder as you work, one of the historians asked if you took the effects of resonant harmonics in your calculations. Oops, we did not. After updating your model, turns out an antinode occurs at any grid position exactly in line with the two antennas of the same frequency, regardless of distance. This means that some of the new antinodes will occur at the position of each antenna, unless that antenna is the only one of its frequency. So what they're basically saying here is, given these two antennas, we have antinodes going all the way out until we run off the edge of the map. These also themselves become antinodes, because the distance from this one to this one is an antinode, right? So they need to go in both directions. So here we have this T and this T go this way, this T and this T go that way. So we have now, basically, we need to know whether or not we just need to walk and set multiple antinodes. Okay, so given our original, now we have 34 antinodes, right? This is now, we can see lots of antinodes here. So for example, these two A's that are next to each other create a line of antinodes all the way across the map from corner to corner, including on top of this 0, which also would have been an antinode just for itself with this 0 and this 0 going that way. All right, so that's our evolution. That doesn't seem too bad. Is our API going to need to change? I don't know. Let's take this API and put it down here. But what do we need to do per antenna pair, right? So we need to know the offset. We still need to know the offset. The first thing we're going to need to do is we're going to need to set an antinode at location 1, and then we're going to need to continually go in the positive direction until we run off the edge of the board. Well, how do we know when we run off the edge of the board? We don't, but that's pretty simple, right? Because we could just turn this into a Bool returning function, right? And then say, if you're not valid, you return false. But if you are valid, we do this, and then you return true, return true. Cut that out. Okay. So we evolve this just to say, did I actually set it or not? So then I'll know when I've run off the edge. So given this, and I want to keep going in this direction until I run off the edge, That's a loop, right? So let's say while grid set antinode of location is true, we're just going to move this location by its offset, right? And then we're going to do the same thing with location 2, except of course, we're going to do location 2 and we're going to go in the other direction. That seems pretty simple to me, right? That's a pretty simple change. Does that turn our 14 into 34? Let's unskip you and see. It does. Okay. And does that turn this into 1246? It does. Okay. So we didn't really need to evolve our design here, but I mean, we could have, if for example we wanted to, we could have said grid set antinodes instead of antinode, and given location 1, and we have an offset. And then we could say grid set antinodes location 2, and then like a negative offset. And we could have pushed that into the grid class to do the walk for us. But first of all, we don't have this notion of inverting the offset yet, so we would have to add that. The alternative is we could go back to the version where we had offset 1, right? And then we could do offset 2, because the way we would invert this, obviously, an easy way to invert this is put them in different directions. So now we would have set antinodes for those two offsets. I don't feel like that really adds much to what we're doing here. Like I think the way we had it was good enough. You know, I'm happy with that. So let's go ahead and do that and bring this back. And then we're good to go. Okay. So I think that is a pretty good place to end today. It was a little bit different than what we've done in the past in that what we did was we weren't sure what the design of the thing should look like. In the past, what we've said is, you know, you're trusting in me, having done this before, to tell you what the design of this thing looks like. Well, the reality is what I did in the first time I did this was the spike, right? And then I went away and I thought about it and said, well, what are the interesting lessons we can take away from this? Because honestly, the algorithm didn't change, really. You know, it changed a little bit, but the data representation didn't have to change at all. And so you took my knowledge as the spike, and then we used that to define the steps that we were going to take in TDD. So today, instead, I showed you the spike and then we evolved the design in real time based on the spike, based on the test that we wanted. Remember, one of the most important aspects of TDD is that you're designing the API of what you want, right? Test-driven development is a design activity more than it is a testing activity. Some people like to call it design by example. But the TDD aspects that we used in the past, we could have used those today. But what I really wanted to do is I wanted to focus on that sort of evolution from the spike into the production code. You've already seen us do TDD. This was good enough for us to now show you a different aspect of design. This is almost more of an acceptance test-driven design sort of a video, and I just left all the TDD on the floor for you to do later. So anyway, I think that's it for today. Hopefully we'll see you again tomorrow. I guess we'll tell based on what the problem is. Next time.